In this video, we're going over the practice test for complex numbers. As usual, make sure you got your formula sheet on you and make sure you got a calculator as well. Let's make a start. 2z plus w. So if we look at this one, 2z plus w is going to be 2 lots of root 3 plus I plus the w, which is 2 root 3 plus 4i. If we expand that out, we're going to get 2 root 3 plus 2i and 2 root 3 plus 4i. If we combine those, you're going to get 4 lots of root 3 for the real bit, and for the imaginary bit, you're going to get 6i. W plus w conjugate. Now the conjugate is the same thing as w, but you flip the imaginary bit. So there's w, and then w conjugate is 2 root 3 take 4i. The imaginary bits will cancel, so you're left with 4 root 3. Find z in polar form. So we need to do two things here. Mod z is the real bit, so root 3 squared, and then the imaginary bit. So 1 squared. That's going to give you 3 plus 1, which is root 4, which is 2. Argument of z, because we're in the top right quadrant, because they're both positive, it's literally just going to be inverse tan of the real bit over the imaginary bit. Now, other way around, imaginary over real. So if you've got a unit circle on you can work that out. If you've got a calculator, depending on what type of calculator you have, it'll show you the actual tan value. Make sure you're in radians for this up the top. And if you're not in radians, you go setup, down to angle, swap that to radians. Inverse tan of 1 over root 3. Let's make sure we get all of our bracketing correct. Cool. Is pi over 6. Therefore, z is 2 cis of pi over 6. Now I want to show you a couple ways to check this. One way is to go into shift setup, change the imaginary mode to r theta, and you can literally just type root 3 plus I. If you do this, it should spit out what the number is in polar form. 2 is the modulus, and 1 over 6 pi is the argument there. 2 cis pi over 6. I'm going to swap it back to a plus bi mode, and the risk that you take with checking it this way is just in case you forget to swap it back. The other way that you can do it is you can type 2e to the power of I pi over 6. And if we know Euler's form, this thing that I've typed here means 2 cis of pi over 6. And you get root 3 plus I. So we know where we're at. Hence find z cubed. So z is 2 cis of pi over 6. Z cubed is going to be 2 cubed cis of 3 pi over 6, which is 8 cis of pi over 2. Now I know it asked for it in polar form, but if you're curious, this is 8i in Cartesian form. Sketch z and z cubed. So z is 2 cis of pi over 6, and in particular it's root 3 plus I. So I might have my scale 1, 2, 3, 4, 5, minus 5, minus 5, and 5 up there. Z is root 3 plus I. So if we get an approximate for root 3, that should give us a good idea where to put Z. So it's across 1.73 and it's up 1. So Z lives about there. Might actually do that in a different color, just so that we don't get confused. So there's Z there. And Z cubed lives up there. Cool. All right, now don't forget to do this bit over here. Comment on the relationship geometrically. So if we want to make a comment on that, we can. The length of Z cubed is the length of Z, or cubed, right? The angle made with the x-axis argument of z cubed is 3 times the argument of z. So something like that. Just talk about the length and the angle, how both those things are affected. Okay, simplify this. It is 20 cis of pi plus 3 pi over 4. And if you're comfortable with fractions, that's going to be 7 pi over 4. You can think of this as pi plus 3 pi over 4. Getting them both over 4, that would be 4 pi over 4. So you do get 7 pi over 4. If you're not sure, check it on a calculator as well. Okay, evaluate I to the power of 1002. I to the power of 1002. You've got to get it to its nearest multiple of 4, so that's 1000. And we're timesing that by I squared. I to any multiple of 4 is just 1. And I squared is minus 1, so we get minus 1. I'm not sure whether your calculator will tell you the answer to this, but we can check just to make sure that we're correct. So if we look at that, I'm going to go shift I to the power of 1002 minus 1. Simplify that. So this thing here is going to be 8 to the power of a third, and you're going to do a third times the angle. So 8 to the power of a third is 2. If you're not sure, check it on your calculator. 8 to the power of a third. See what we get. It's 2. And then a third of pi over 2 is going to be, cool, so just like that. All right. Convert that to Cartesian form, giving your answer with exact values. So if we work this out, so we can write it as 4 cis of minus 2 pi over 3. That's going to be 4 lots of cos minus 2 pi over 3 plus I sine minus 2 pi over 3. Now we can have a look at this on a unit circle if you want. That should give you the correct values. But if we want, we can go cos of minus 2 pi over 3. Just make sure that we're in radians before doing this. Something like that, minus a half. And then I sine of minus 2 pi over 3. So if we look at that, sine of minus 2 pi over 3 is what we want. There we go, you get root 3 over 2, and it's negative as well. If we times everything by 4, that's going to give you minus 2, take 2 root 3. And I should have an I in there as well, shouldn't I? There we go, I. Cool. One thing that you can do if you want, so you can go 4e to the power of I, and then you can look at minus 2 pi over 3. And you get what I said. Cool. Same thing here, we can preempt what this one's going to be. 2e to the minus pi I. We can just work out minus 2. But let's see why. So 2e to the minus pi I is 2 cis of minus pi, which is 2 lots of cos of minus pi, plus I sine of minus pi. Now, cos of minus pi is going to be minus 1. And then I, lots of 0. So you get minus 2 as your answer there, which is what our calculator said. Let z equal r cis theta, find z over z conjugate. So z is r cis of theta. Z conjugate is r cis of minus theta. Now, if we think about why this is true, with z, we're making sort of an angle with the x-axis. So there's r, there's theta, and that is z. Now, if we look at z conjugate, it's going to be down here. So that would just be minus theta as the angle, it would still be r. So if we look at working this out now, z over z conjugate, so it's going to be r cis of theta and r cis of minus theta, which is r over r gives you 1, and this is going to be theta take minus theta, because that's how dividing polar form works. So you're actually going to get cis of 2 theta. Cool. All right, do that. So this is very similar to what we were doing before. Z over W. So let's see what we get here. It's going to be 5 cis of pi over 4 on the top, and it's going to be a root 5 cis of pi over 6 on the bottom. So you get 5 over root 5 as the modulus, and you're going to get pi over 4 take pi over 6 as the argument. Now 5 over root 5 is just root 5. You can check that on a calculator if you want. Or if you want to do it by hand, you can go 5 over root 5. This is going to be root 5 times root 5. That's what 5 is. You get root 5. There's a million different ways to do that. You can use index laws and stuff. You can times by root 5 on the top and the bottom instead, but you will get root 5. Now, when we're dealing with the pi over 4, take pi over 6. So you can think of this as 3 pi over 12. Take 2 pi over 12, because we cross multiplied that by 3 over 3 and that by 2 over 2 to get a common denominator of 12. So we're going to get pi over 12 just there. So that is this pi over 12. Okay. Now, one thing that's really good to do, just to make sure that you're not like doing fractions wrong or anything, you can stack these fractions up, so you can get pi over 4, take pi over 6, and we'll see what we get there. Hopefully it's pi over 12. I'm not very used to using the stacked fractions on a Casio. Still getting used to that. Yeah, pi over 12. What's the smallest positive integer such that it's purely imaginary? So we've got this sort of hanging out here at pi over 12. And ideally what we'd like is that it hits this axis here. All right, so yeah, it's got to hit this imaginary axis here. So we want pi over 12 times something to essentially give you pi over 2. That would be the angle. So that something is 6. So like z over w to the n is going to be root 5 to the n cis of n pi over 12. Therefore, n is 6, gives purely imaginary. That's the smallest way you can do it. The next value would be like n is 18, and that would wrap it all the way around to the negative imaginary axis there. That would also work. Now, how do we check? I always like to double check. So one thing that you can do is you can work out these original z and w's. So z is, if we use Euler's form, 5e to the I pi over 4. It's just a quicker way of writing cis, really. I'm going to see what that equals, and I'm going to use this little arrow to store it in z on the calculator, say alpha z. So now every time I use z, that'll come up. W, I'm going to do the same thing. So if I look at root 5, e to the I pi over 6, I get an answer there, and I can store that in W. Yeah, a couple of things. If I look at Z over W, I get that number there. And we can use our little trick that we saw before to get it back into polar form. Just use that. So if I try and do Z over W now, hopefully, yeah. So we know we were correct about part A. That's good news. And if I look at, let's convert it back to real form. Cartesian form. If I look at Z over W to the power of 6, I'm hoping that it's purely imaginary. So let's try that. Z over W power of 6. Groovy, 125i. So we know we're on the right track there. And for example, if I look at something smaller, like let's go Z over W cubed, you'll see that it will have a real bit in it, which is not what we wanted. There we go. So it's worth using those that little store trick to check your answers. It's pretty good. This here is a circle. It has got a center of 3 take 4i, and it's got a radius of 2. So if we put our scale here, 5, 5, minus 5, minus 5, 3 take 4i is sitting here, and it's got a radius of 2. So all these points here will be on the outside of the circle. There we go. Label it with the equation. Z take 3 take 4i is 2. This one here, minus pi over 4 is less than the argument, z is less than pi. So this line here would be the line where the argument equals pi, and minus pi over 4 would be like 45 degrees down this way. Notice that I've done a dashed line for this bit because it's a less than sign, and I've done a solid line when it's equal to. That's really important that you do that. And we'll highlight it in, so not like that. So yeah, it's all this region in here. Apparently I can't highlight. It's all this region in here that you want highlighted. All right, remind me not to highlight stuff on a PDF, but there we go. That's the region you'd like. And I guess we should label that region with what it actually was. So minus pi over 4 is less than argument z less than pi. Wonderful. All right, show that it's that in polar form. So let z equal, I might use a different letter because we're about to use z there. Let's use w. W is not in use. W is minus 4 plus 4 root 3 of I. Mod w is root of minus 4 squared plus 4 root 3 squared, which is going to give you a square root of 16 plus 3 times 16, 48, which is going to give you a root of 64, which is 8. So that's good. There's mod w. Argument of w. Now we've got to adjust it. So usually what I do with the arguments is we calculate this angle phi. Now this is inverse tan of the imaginary bit over the real bit, and you make it positive. So I'm going to put bars around it. That means you make it positive. If it's in the top right quadrant, you keep phi. Down here it's minus phi. Up here it's pi take phi, and up here it's phi take pi. Whatever quadrant you're in, you just adjust that. So for us, phi is inverse tan of 4 root 3 over 4. I'm just going to keep everything positive. So maybe what I'll do there is I'll just change the bars to be around the imaginary bit and the real bit there. Which is essentially just inverse tan of root 3, because the 4s will cancel, and we can see what we get there. Should hopefully be a nice-ish number. There we go, pi over 3. Well, that's good. So there it is. Therefore, argument of w is going to be, since we're in the top left quadrant, it's pi take pi over 3, which is 2 pi over 3. Therefore, w is 8 cis of 2 pi over 3. And we've done it. We've shown that it's that in polar form. Hence, find all solutions to that. Now, the reason I asked you to find it in polar form is we can say z cubed essentially is 8 cis of 2 pi over 3. Now, this is going to be from A. Now we need to add on 2k pi there because it can be plus any multiple. We cross multiply. So we're going to go 8 cis of, now this will be 2 pi plus 6k pi all over 3. Really important, we haven't done the cube root yet. We're about to do that now. So z is going to be the cube root of 8 cis of 1 over 3 times all that stuff. So 2 pi plus 6k pi 3. If we work out what all that is, it's going to be 2 cis of 2 pi plus 6k pi all over 9. Wonderful. All right. So let's plug in our k values and we'll see what we get. So I might do this in a different color just to keep it separate. K equals 0 almost always works. So this is going to be 2 cis of 2 pi over 9 when you plug in k equals 0. K equals 1 usually works. So you get 2 cis of 8 pi over 9. If you try k equals 2, that'll be too big. And the way that you can tell is the argument there needs to be less than pi. So if that number on the top gets bigger than 9 pi, we're in trouble. But k equals -1 will work to give us our third solution. And since it's a cubic, we expect 3 solutions. Okay, the last one is 2 take 6. So this is going to be 2 cis of -4 pi over 9. Now you can imagine going left even further, you would get 2 cis of -10 pi over 9, but that would be too big. So these are our 3 solutions. I want you to label them as Z1, Z2, and Z3. Z1 has the smallest positive argument. So really crucially, this one here is Z1. Z2 has the next biggest argument, and Z3 wraps around again to be that number there. Okay. Sketch your answers on the argand diagram below. So probably not a bad idea to pop in your scale. We don't need our scale to be too big. We're just going to go 1 there. And let's get some approximates for this, just to know we're definitely putting them in the right spot. So easiest way to get an approximate for a cis like that is to go, instead of using cis form, use Euler's form 2ei to the 2 pi over 9. And that should give you a nice Cartesian form approximate right away. Okay, see what we get there. 1.53 and 1.28. So Z1 is going to live just here at 1.53 and sort of up here at 1.28. Not there. There is Z1. I'll do it in a different color to our scale so that we don't mix that up. There's Z1. Conveniently, well, Z2 is not quite going to be in the right spot. Let's get an approximate for that. So we can change this to be 8 pi over 9 minus 1.87 and 0.68. So that's going to live sort of here, roughly. Doesn't need to be perfect. It just needs to be like you've at least tried to put them in the right spot. And if you were like, if that was sitting over 1, like in the imaginary bit, I'd be a bit concerned. 2 cis of -4 pi over 9. So if we get an approximate for this, .347 and minus 1.96. So we're probably looking at something down there. Let me make sure I got that right. 3.4. Probably a smidge over more to the right. There we go. Now we're used to this in sort of like roots of unity question where they're all like cube roots of 1, which is very nice. This still does make a lovely shape. It's still like an equilateral triangle. So don't worry too much about it, but like it's an equilateral triangle if you join up all the edges. It's just that it's being rotated a little bit, that's all. All right, next up we've got to show these two things. Now let's just refresh ourselves on what Z1, Z2, and Z3 are first. So this was 2 cis of 2 pi over 9 from above. Z2 was equal to 2 cis of 8 pi over 9. And Z3 was 2 cis of -4 pi over 9. Now we got to show these things. Now, what you want to do is start from the messy thing and work your way left. In maths, we like to simplify equations. It's not very natural to make equations messier. So it tends to be easier to work from the messier thing and get down to, hopefully, Z2. Okay, Z1 to the 4 over 8. So we're looking at 2 cis of 2 pi over 9, all to the power of 4, all over 8. So this is going to be 16 cis of 4 lots of 2 pi over 9, all over 8. So 16 over 8 is 2. And 4 lots of 2 pi is 8 pi over 9. Hey, what do you know? That's Z2. Good. 8 over Z1 squared. Okay, I might write 8 in polar form here just to help us along. You'll see why in a second I've done that. And then we've got Z1 squared on the bottom. So this is 2 cis of 2 pi over 9 squared. By the way, if you're wondering why 8 is in polar form, 8's a real number, so it's sitting down there. Got a length of 8, and it's got an angle of 0. That's why it's 8 cis of 0. Okay, let's square the bottom of this. So you're going to get 4 cis of 4 pi over 9. And on the top, you're going to get 8 cis of 0. How do we deal with this? We do 8 over 4 is 2. And we got 0, take 4 pi over 9 there. This gives us a 2 cis of minus 4 pi over 9. What do you know? That's Z3 as required. Cool. Alrighty. Now, I'll level with you. The rest of this question, the whole point of it is to prove that this thing hopefully equals 0. It's actually quite a general truth about cube roots. So I'd encourage you to think about like generalizing this proof here so that instead of using a specific number here, we're just sort of using any complex number. But that can be like a little challenge question. Let's do it for this example. So K is Z1 plus Z2 plus Z3. We'll start there. So if we look at using what we just had in our previous question, Z1 is Z1. Z2, we've actually just proved Z1 4 over A. So we're going to be using that. In tests or exams, it's a good idea to refer back to previous parts. It usually becomes relevant again at some point. So this is from part D. That's why that one's true. Now, notice that on the left-hand side of the equation in the show that, we've times by 8z1 squared. So I'm going to be timesing by 8z1 squared on both sides. So I might just write times by 8z1 squared to both sides. Just so it's really clear, because it's a show that question. We're going to get 8z1 cubed for that first term. This next term will become z1 to the 6 because the 8's will cancel off. I might actually write it in 2 steps, so that's 8z1 to the power of 6 over 8. This last term will become 64z1 squared over z1 squared. If we simplify this down, I get 8z1 cubed. The 8's cancel off here, so I get z1 to the 6. And here I get just 64. And this is 8k z1 squared, just swapping the order of those things. And I think we've done it. So we'll just swap the order, like rearrange. So z1 to the 6 comes first because it's a polynomial. We like to write it in decreasing order of the powers. So this is 8k z1 squared. Wonderful. Alrighty. By the way, I won't lie, this is quite a difficult question. So if you had trouble with it, that was the point. Hence show that k equals 0. Use Cartesian form. So we already know what z1 cubed is. Z1 cubed is this number here, minus 4 plus 4 root 3i. Because remember, Z1, Z2, and Z3 were all solutions for this possible Z value. Z1 cubed is that number there. So, Z1 cubed, I might just make a note, is minus 4 plus 4 root 3i. Okay. So, 8k kz1 squared is, we'll just start off from here, z1 to the 6 plus 8 lots of z1 cubed plus 64. z1 to the 6 is going to be z1 cubed squared. And now we can just plug in what z1 cubed is. So it's minus 4 plus 4 root 3i. We'll square that. This is minus 4 plus 4 root 3i. And this is 64. You can be a little bit cheeky and get this first bit in a calculator. But since it's a show that question, we'll do it to double check that we're right. But so minus 4 plus 4 root 3i. Square that. So yeah, minus 32, take 32 root 3. But the way to do it properly is to do the first bit squared. You're going to get minus 2ab. So minus 2 lots of 4 and 4 root 3i. Then you're going to get the last bit squared. And then we'll expand the 8 into this stuff. So take 32 root 3i plus 64. So that's 16. All that times together is 8 times 4, so 32 root 3i. That 4 root 3i squared is going to be 16 times 3, so that's 48i. Let me make sure I've got that. 48i squared. I squared is minus 1. Take 32. That should be a plus. No, it shouldn't. It's a minus. Take 32. Take 32 root 3i plus 64. Now let's collect up all of our real bits and then all of our imaginary bits and see what happens. So if we color code this, we've got 16, take 48, take 32 plus 64. What does that equal? 0. If we collect up all of our imaginary bits, minus 32 root 3, and that should have been a plus when I did the algebra there, because it's 8 plus. So the imaginary bits will also cancel out as well. 0 plus 0i. Beautiful. So it's 0. Okay, let's grab some space over here. Therefore, 8k z1 squared is 0. And by the null factor law, hold on, have we got it? Didn't show that k is 0, yeah. So by the null factor law, we've got 3 possibilities. 8 is 0, which doesn't work. K is 0, which is what we wanted. Or z1 squared equals 0, which doesn't work as z1 does not equal 0. It's like 2 cis of 2 pi over 9 or whatever it was. So by null factor law, only possibility is k equals 0. Wonderful. All right, good. Hence calculate that. This is just to check your understanding of what we've just proven. We've learned z1 plus z2 plus z3 is 0. Therefore, 2 cis of 2 pi over 9 plus 2 cis of 8 pi over 9 plus 2 cis of minus 4 pi over 9 equals 0. Therefore, cos of 2 pi over 9 plus cos of 8 pi over 9 plus cos of minus 4 pi over 9 equals 0 to make the real part equals 0 in star. And we just call that thing star. Done. So this expression here is also true for sine as well. If you do sine of all those values added together, you get 0, because then that would make the imaginary part equal 0. What a fun question. Again, don't worry if you had trouble with that. Practice makes perfect, and That is an example of the curveball A-level question, which we might see. Okay, hopefully a nicer question, this one. There it is. We just got to get the equation of the function. This here is a stationary inflection point, and I do say that in the test as well. So you've got z take 1 cubed is a factor. So if you ever have like cutting through at like k, you'll get z take k. If you ever have it just touching at k, you'll get z take k squared. And if you have this, you'll get z take, in our case, 1 cubed. The other factor is z plus 2. And this is f of x. I keep using z's rather than x's. X take 1 and x plus 2. This is f of x. Now, there's one more step. We have a scaling factor a that could stretch or squidge our polynomial. And we just need to plug in the point that we know. So we know 0 minus 1. So we're going to be plugging in minus 1 and 0 for the x bound. So we'll just work that out. A, lots of 0 take 1 cubed and 0 plus 2. So this is 0 minus 1 into equation. So minus 1 is A, lots of minus 1 and 2. So minus 2A is minus 1. Therefore, A is going to be 2. No, it's not. It's going to be a half. Therefore, f of x is going to be a half, x take 1 cubed, and x plus 2, just like that. Now, we better actually check that this is right. So if we go and graph this on a calculator, do check this, because you're basically throwing away marks if you're not. So x take 1 cubed and x plus 2. There it is, and it appears that it's, barring a window change, appears it's pretty spot on. There we go. Wonderful stuff. Is it possible for it to have any more x-intercepts than the 2 in the picture? No. So this is a fundamental theorem of algebra question. It's asking about your understanding of x-intercepts. So I've told you before that it's a degree 4 polynomial, or a quartic. So as f of x is a quartic, I'm going to type this. As f of x is a quartic, it has at most 4 x-intercepts. Alright, so we already have all 4. All 4. One counts as 3 zeros, or x-intercepts, because it's like a triple factor. Also, complex zeros coming in conjugate pairs. So even if some were hiding, there wouldn't be 3 of them. There would have to be an even number. So even if for some reason you didn't count that this was like a triple intercept here, we expect to have 4 intercepts, and so the complex ones always have to come in pairs, so it's not going to happen because we need 3 missing ones if that was the case. Okay, let's move that back down and we'll move on. Apologies about that. There we go. All right, next up we have a polynomial division question. So what will the remainder be divided by x plus 2? The remainder is p of minus 2. So what you plug into the function is whatever makes that thing equal 0. If x was minus 2, it would make that thing equal 0. It's going to give you, and by the way, this is by the remainder theorem. This is going to be minus 2 cubed plus minus 2 plus 7. This gives you minus 8 take 2 plus 7, which is going to give you minus 3 as the remainder. Now we're going to actually just check that we were correct by using the division algorithm. Or I guess the remainder is a good way to check that we did the division correctly. X plus 2, this polynomial we're dividing by is x cubed plus 0x squared. So you've got to have that x squared term in there, plus x plus 7. if we divide by x plus 2, our first term is going to be x squared times x squared by both bits. You're going to get x cubed for the first term and 2x squared for the second term. Subtract those off from each other. You're going to get minus 2x squared there, plus x there. So then we just got to rinse and repeat. Minus 2x is our next term. So if we do that, then we're going to get minus 2x squared there. And then we're going to get take 4x. X take minus 4x is positive 5x. Bring the 7 down, plus 7. So we're going to get plus 5 just there. Then we've got 5x plus 10 when we times that 5 into both bits. And so then if we subtract these, we should see that our remainder is minus 3, which is what we would expect. So p of x, or I might actually write it out in very, very full what p of x is as well. X cubed plus x plus 7 is the quotient. So the quotient is x squared take 2x plus 5, dividing by x plus 2, and the remainder is 3. And just to be really clear, that's q of x, that's p of x, and that's r. Sometimes people call this d of x, so watch out for that. Cool. And obviously make sure the remainder is the same as what you got in part A, otherwise you've probably done something wrong. State one more 0 of this polynomial. The other 0 is to take I, the conjugate, by fundamental theorem of algebra. Capital A, I guess, seems important. Cool. If this passes through 1,8, find the equation of p of z. So we've got, I like to sometimes keep my list of zeros and then the corresponding factors to them. So one of my zeros is minus 1. So z plus 1 will be a factor there. One of my zeros is 2 plus I, and the other one is 2 take I. Now, technically, the factor here is going to be z take 2 plus I, and this one is going to be z take 2 take I. And you could FOIL those two out to get the quadratic factor. But we have a more efficient way of doing this into a quadratic factor. Out of these two here, the sum is 2 plus I plus 2 take I, which is 4. And the product is 2 plus I times 2 take I, which is going to give you 2 squared take I squared, which is 5. So that will tell us that the factor that we're looking for is z squared take the sum, so take 4z plus the product. So that's how we do that one there. Now we can write out what p of z actually is. So p of z is going to be, let's do it in blue, why not? P of z is these three factors. So it's z plus 1, and then it's z squared take 4z plus 5, and you've got to have a scaling factor out the front, a. How do we find a? Well, I've given you a point. So we're going to plug in 8, and then we're going to plug in 1 for the z value. 1 squared, take 4 lots of 1 plus 5. So 1 plus 1 there, a equals 8. So sub in 1, 8, just like that. Okay, so 8 is going to be a with 2. This one in here is also another 2. Therefore, a is 2. Okay, so a couple things that we can do here to check. First of all, let's just write out what our polynomial is. So it's 2 lots of z plus 1, z squared take 4z plus 5. Just like that. We can graph it. So we'll have a look at that. Graph. Delete out all of our other graphs. All right, now hopefully we have a couple things. Hopefully we have an x-intercept at -1, which we do. And hopefully if I go shift trace 1, I should get 8, which I do. Poly solving this is a bit tricky because it's not expanded. So we're just going to have to trust z squared take 4z plus 5. Or I guess what you could do is you could do poly solve on just the bit in there. So a degree 2, 1, -4, and 5. You should get solutions 2 plus I and 2 take I, like I've said. If polysolve doesn't show that for you, you need to go shift setup and make sure you're in that complex mode. Okay. All right. X take 1 is a factor of f. Find 2 possible values of a. So therefore, 0 equals f of 1. And this is by the factor theorem. It's a special case of the remainder theorem, actually. It's for when the remainder equals 0. We have a factor. So 0 is a squared plus 1 times x is 1. And then we're going to get 1 take 2 to the n plus 2a. Let's see if we can simplify that down. So a squared plus 1. And then we're going to get -1 to the n plus 2a. So they're saying there should be 2 possible values of a. So it might depend on what n is as well, because whether or not n is even or odd will impact things. So n even and n odd. We're going to break this up into 2 cases. If n is even, we get 0. This is positive, so it's a squared plus 1 plus 2a. So a squared plus 2a plus 1. You can actually sum and product this. A plus 1 and a plus 1 works. So therefore, a is -1. Or if you want, you can get polysolve on the case. Menu, equation mode, quadratic. So it's degree 2, 1, 2, 1. Should give us -1. There it does. If n is odd, we're going to get minus a squared plus 1 plus 2a is 0. So 0 is minus a squared plus 2a take 1. I'm going to pull minus out as a common factor. And then we can also sum and product this. So it's going to be a take 1 and a take 1. Therefore, a is 1. Again, you can polysolve that if you want. You could look at -1, 2, or -1, and you should get +1 for your answer. All right. Suppose now that we already knew, and it has a remainder of that, find the values of a and m. So -164 should equal f of -1. That's what it's saying by the remainder theorem. So let's see if we can calculate what f of -1 is. So this is going to be a squared plus 1. X is -1. It's going to be -1 take 2 to the n. And then it's going to be plus 2a. Okay. So that we can probably simplify down a little bit more. So this is going to be a squared plus 1. I'm going to get -1, and then I'm going to get -3 to the power of n plus 2a. Now this looks pretty bad, but remember we can break it into the 2 cases. So if n is even, then immediately we have a as -1, and we'll see what we can do with that. So -164 equals all that. So we're going to get -1 squared, because that's the a value, plus 1, -164 equals -1 squared plus 1 times -1 times -3 to the power of n plus 2 lots of -1. And we can sort of just work with this. So this is going to give you -164. We're going to get 2 with -1 minus 3 to the n. Take 2. I can add 2 to both sides, so I can get -162 is going to give us, let's see, -3 to the n, we don't know, but we do know that this is -2, lots of -3 to the power of n. 162 over 2, we can work out what that is. So we'll just go into normal equation mode. There's going to be positive 81 over here, which is minus 3 to the power of n. Now, if you want, you can actually do a log here. I've forgotten how to get to log. It should be in math. Log AB, yeah, there we go. We're looking for log base 3 of 81. Now, you might spot that it's 4. But basically, n is 4. Now, does this make sense with the negative? Yes, it does, because minus 3 to the power of 4 is good, and n is even, so that's good. So we found A. A was minus 1 and n was 4. Let's look at if n was odd. I'm assuming something breaks because it says just find the values. We get minus 164. So by the way, A has to equal 1 in this case because we showed that up there. Minus 164 gives you 1 squared plus 1. You get minus 1 for the x value. You get minus 3 to the power of n plus 2 lots of 1. And we'll just keep churning through this algebra. So you get 2 with minus 1, minus 3 to the power of n plus 2. So let's subtract 2 from both sides. You're going to get minus 166 is 2 with minus 1 and minus 3 to the n. We can halve everything. So if we go for 166 over 2, it's 83. So you're going to get 83. The negatives will cancel as well. Minus 3 to the power of n. Now, n is in z plus. N's a whole positive number. I don't even know if we can. Let's see if we can work out what log AB, so there it is. What do I raise 3 to the power of to get 83? That number, 4.022. But that makes me very upset because it doesn't work. First of all, if I look at minus 3 to the power of the answer there, your calculator hates it because it doesn't like doing negative numbers to powers unless those powers are even whole numbers. So there it is. So no. These are the actual solutions. A is minus 1 and n is 4.